So Arthur SNIA is co-chair of the SNIA Persistent Memory and NVDIM Special Interest Group, which accelerates the awareness and adoption of persistent memories and NVDIMs for computing architectures. Arthur is also the Director of Product Marketing at Smart Modular Technologies, where he's been driving new product launch and business development activities since 1998. Please join me in welcoming Arthur.
Good morning, everyone. How's everybody doing? So again, my name is Arthur SNIA. I'm the co-chair of the Persistent Memory and NVDIM Special Interest Group for SNIA. Been doing that for about 3 or 4 years now. And this morning I'll talk about persistent memory and its association with artificial intelligence and machine learning. So I'll move this a little bit here. So the data creation, tons and tons of data creation, and these systems that are in use today aren't really equipped to handle the fast processing that is required by artificial intelligence and machine learning. So hence the need and growth for persistent memory. It's been emerging for the last 10 years. It seems like it's taking a long time, but maybe from the outside it's faster, but on the inside it seems like it's taking a long, long time. But anyway, we'll talk about persistent memory and its association with artificial intelligence and machine learning. All right, so today the dominant technologies are DRAM and flash. DRAM is volatile. It has certain densities associated with transforming data and analyzing data in a fast manner. And then on the other side we have NAND flash. So it's slower, it's block addressable, but it's non-volatile. So both technologies have their benefits, but there's been this gap in the middle, and that's where persistent memory has come in. So what is persistent memory? Persistent memory is byte addressable, it's fast, and it's persistent. So there's a number of technologies and actually conferences specifically targeted toward persistent memory. There's trade-offs between the different types. There is persistent memory media interfaces that are emerging and interconnect standards, and I'll talk about some of those. They're in the form of DIMMs, NVDIMM-N, I'll talk about that. Also NVDIMM-P is emerging. There's also other forms of persistent memory, Optane memory from Intel as well. And those all have their place to help fill this gap and help support AI and machine learning applications. So the persistent memory tier in the middle there, you can see in the orange, between the CPU and there's memory on top, storage on the bottom. This gap is being filled by various types of persistent memory, and the main reason is for system acceleration. So we're trying to process all this data as fast as we can in memory, but then not have the risk of losing it due to a system crash or other factors that may impact all that activity. So high capacity persistent memory, if you can put all your database completely in persistent memory and work on it there at high speeds without the risk of losing it, you're dramatically accelerating system performance. So that's the reason for persistent memory, and it's been growing. Instant byte level persistence enables new database algorithms for storing machine learning data sets. I'll talk about that as well. So in general, these are the use cases for persistent memory. You can talk about large data sets and in-memory databases, putting it all in persistent memory, as well as other needs like checkpointing, caching, tiering of data that in smaller data sets that ranges between high-performance computing, enterprise and software, defined storage applications, etc. So why persistent memory for artificial intelligence and machine learning? So the idea here is all this data that's being created, it needs to be analyzed, it needs to be processed, it needs to be brought from storage to memory, and the movement of this large amounts of data take a long time. So that the idea is to by using persistent memory, you can accelerate this process and not risk losing it. So running the algorithms with machine learning can dramatically reduce the amount of time, and that's the reason why persistent memory is a good fit for artificial intelligence and machine learning applications. There's also the growth of computational storage. I have one slide, I'll talk a little bit about that toward the end. So the AI training challenges. So the model training takes a long time. So you're pulling data sets from storage and you're working on those data sets. You have to do checkpointing to make sure the data sets are saved in case of a system crash, processing the data, importing it, and moving it back. That all takes a lot of time within the hardware system to take care of that. And if you're making quick decisions, such as in autonomous driving or military applications, many types of applications, making quick decisions and analyzing the data is very, very critical. So checkpointing in particular. Checkpointing, you're saving the database at certain points so that if it crashes, you're able to retrieve that without losing a lot of time. So checkpointing is a critical function for artificial intelligence applications. And the way it's done today, it's done in storage. So you're taking a checkpoint or snapshot of the database and putting it back into the SSD storage drive. And typically, so that's being done in DRAM. You're moving from nanoseconds, like 100 or less than 100 nanoseconds, doing the checkpointing, and then moving that data back to the NAND storage, and that's hundreds of microseconds. So it's 3 orders of magnitude slower. And that hits the performance of the system and being able to make the decisions quickly. So that's the model on the right there. You're moving from DRAM to NAND and doing the checkpoint and maintaining that database. So in the case of the system is lost, you're not going to lose the state of the database. So if you add persistent memory, and this is a key application for persistent memory, which is checkpointing, you're filling this gap in the middle here. So today, there's a number of persistent memory technologies. There's MRAM, there's ReRAM, there's Intel's Optane DIMMs. I'll talk about those. And there's also NVDIMM-N. So that's the function of the group that I'm involved with SNIA. And a few years ago, maybe nobody heard of an NVDIMM, but today, hopefully everybody knows what an NVDIMM-N is. So that's an ideal application where you're putting the checkpointing data. When you plug in an NVDIMM-N into a server that's enabled to see it, it's going to recognize that memory and map it out as persistent. So that's a DRAM, an RDIMM, backed up by flash. And then it's plugged in, it's recognized as an NVDIMM, and that section of memory is mapped as persistent. You can do all your checkpointing, so the application has to be written to do that checkpointing in the DRAM or in the NVDIMM without the risk of loss. So that right there is like 3 or 4x a factor in terms of system improvement time by doing that checkpointing in persistent memory. And eventually, maybe checkpointing won't even be needed because all of it's being done in persistent memory altogether. So it could be something that's eliminated in the future. The other technologies that are shown here, the MRAM I mentioned, that's high speed, that's lower density. There's ReRAM, which is emerging, and there's also the Optane DIMMs. I'll talk about some of these. All right, next is machine learning. So machine learning, you're talking about data acquisition, preparation, model training, running these algorithms on the data sets. And all that is done in DRAM, and then you need to be able to save that in the storage. And again, it takes time running through the I/O, the latencies associated with the I/O, the latencies associated with the NAND itself, and moving this data back and forth. So if you're, again, making quick decisions and trying to interpret data, all this data coming in, for example, with autonomous driving, making decisions, it's going to be slower. So persistent memory helps to accelerate this performance. And that's where this persistent memory on the right, you can see on the top. In this case, it's an SSD NAND drive, and orders of magnitude slower because you're going through the I/O, you're going through the speed of the flash, compared to using a DRAM or other fast forms of persistent memory on the bottom. And that dramatically accelerates the machine learning process by using this persistent memory in the hardware. In terms of the data set sizes with machine learning, you're ranging from kilobytes to terabytes and the various applications that are shown here. So where do those fit in terms of persistent memory, and how can different types of persistent memory be used with these different data set sizes? So first of all, for example, when we're talking about NVDIMMs, those densities range from 16 to 32 gigabytes. Maybe there'll be a 64 gigabyte NVDIMM-N. If you're loading those into a system, you can get up to 192 gigabytes per server. So that means you're enabling these smaller data set sizes to go into those NVDIMMs that have been enabled on these GPU servers. And that's going to accelerate this analyzing process where the algorithms are being run on the data to make those decisions. So the point is to get that data out of the system as fast as possible to make quick decisions. And in the case of the smaller data set sizes, NVDIM-N is an ideal case to do that. So you're reducing the read latencies from hundreds of microseconds to hundreds of nanoseconds. So orders of magnitude, again, faster to make those decisions. In the case of larger data sets, Optane DIMMs from Intel. So those range in densities from 128 gigabytes up to 512 gigabytes. Those are byte addressable. They're high speed, not as high speed as DRAM, but those are mixed on the memory bus with the DIMMs. So they're mixed with DIMMs and the Optane DIMMs in the same slots or similar slots. So now you're able to put larger data sets and do the machine learning all in memory without the risk of losing it. So in this case, you're doing possibly terabytes of machine learning data and going from hundreds of microseconds to about 15 microseconds in the use case for Optane DIMMs. And that is an Intel proprietary type of persistent memory. Okay, so now you have hot, warm, and cold data. And in the case of AI and machine learning, a lot of that is going to be hot or warm data. Checkpointing, machine learning, running the algorithms, that's going to be hot or warm data. And by adding in various types of persistent memory, depending on the system you're using, whether it's Optane DIMMs or NVDIM-N or in the future NVDIM-P or other types of persistent memory that may emerge such as ReRAM or MRAM and put into the system. Now you have this whole tier, many more tiers of places to store this memory based on the application and how to use it. So the systems have this, they're being enabled to support persistent memory. It's a matter of applications and writing those applications to take advantage of this persistent memory. And that's what the Persistent Memory and NVDIM SIG Special Interest Group has been focused on for about the last year and a half now, because it took about the first more than 5 years to get the ecosystem in place. So now we want to focus on applications. All right, so what does an ideal system or a persistent memory optimized server for AI and machine learning look like? So this is just an example here. You have a lot of GPUs in the systems for very high speed access of all this data and getting it out onto the network as fast as possible. You can either use a combination of NVDIM-N or Optane DIMMs, or again, other forms of emerging persistent memory, where this data can be, the checkpointing can be done, or the machine learning can be done in that persistent memory. Okay, so if we look to the future in terms of interfaces and memory standards and so forth, today everything is direct attached to the CPU. You've got NVDIMMs and you've got regular DIMMs attached to the CPU. And there's limitations, as I showed on the hierarchy. There's a gap in performance between DRAM and NAND. So these interfaces are emerging on the right here, such as CXL, Gen Z, C6, and OpenCAPI to help fill these gaps in the persistent, in the connections between the CPU and the storage. And what these interfaces are doing are expanding ways that memory or storage or persistent memory can be connected into the system and be cache coherent. So it can, the host system can see and recognize what's being plugged in to that host system and take advantage of it. And applications will need to route data accordingly based on how it's being used and what is needed based on these different interfaces. So a lot of work going on there. There's different symposiums that support these different technologies. It's a very interesting time to be going into here. And the last point on the bottom here is that a lot of new types of products are going to emerge, and interconnects and form factors, not only DIMMs or NVDIMMs, -N, -P, there'll be PCIe cards, there'll be other connector options on the right there on the top to be able to connect different types of memory, persistent memory and storage onto a system to take advantage of higher speeds and newer technologies and higher bandwidth and lower latency. All right, so one slide on computational storage. SNIA has a computational storage technical working group, and the idea here in terms of support for AI, an example would be doing metadata, creating the metadata on an SSD. So you have a smart controller that does the processing of that data on the SSD itself. So you're helping to offload the CPU and do this activity in the SSD. So that's the growth of the computational storage group. I encourage you to take advantage of that. We're out in the booth back here if you have further questions about that. Persistent memory standards are very important. Without standards on the interface, the technology, the host systems being able to recognize what these particular memories are and take advantage of them, it's just a waste. So it's taken a long time for these standards to emerge. On the top, we have SNIA, which SMART is a member of the SNIA organization. They have the NVMe programming model. And this is designed to have tools and support and all the enablement efforts to take advantage of persistent memory, and that's all open to be used. We have JEDEC, and JEDEC is developing the hardware. The NVDIMM-N was standardized in 2018, October. The NVDIMM-P is being worked on now, and the idea is to get all this work done in advance for everyone to take advantage of it. And then on the bottom, these new interfaces and interconnect standards that are emerging as well. All right, so I'd like to ask Jim Pfister to step up. He's going to talk about our NVDIMM programming contest.
Thank you very much. All right, so this is cool. And as a software geek and as a hardware geek, I mean, I get excited about the fact that we've got new technologies and we've got new fun things to play with. I talk to so many people that say, wow, you know, I remember 20 years ago and all that technology is really cool. There's new technology coming out all the time. Persistent memory is a great opportunity for all of us to really get involved in something that is really going to change the game, not only in terms of compute, but in terms of the way that systems are built and architected over time, both hardware and software. So from this perspective, persistent memory is a great opportunity for everybody. What I would say is we get a lot of pushback on, well, this seems really hard. It's a new memory model. We're going to have to understand how to program it. SNIA has done a lot of work for you. SNIA, the technical working group for persistent memory, actually worked with the OS and VM vendors to build a common verbiage model for programming. So if you want to program in Linux, if you want to program in Windows, if you want to program on top of a VM bare metal, you have the ability to use a common model. And even better, we've actually worked with the open source industry to be able to deliver an open source toolkit. And that open source toolkit is the Persistent Memory Development Kit. You see it there, PMDK. If you're, I should have put the link on the slide, but it's pmdk.io. If you go there, you can actually get the Persistent Memory Development Kit and you can start working. You have the ability to actually run that and install that on a system without persistent memory, and you can model it through emulation. But you can find you can actually get access to systems if you want as well. You don't just have to use PMDK. There's direct programming models that you can do. You can build your own embedded environment, and I know a lot of the smart customers have already done that. And there's some other similar Windows and Linux architecture models that you'll find out there if you do some Googling on persistent memory programming. What we as SNIA really want to focus on, though, is developing some experience opportunities for you to be able to develop. So, first of all, we've been doing a series of persistent memory hackathons for about the last year. We've done 8, 4 in the US, 4 otherwise internationally. Well, 3, the 4th one coming up in Beijing soon. We also are currently doing an NVDIMM programming challenge. So if you stop by the SNIA booth, I can get you information on that. Or you can see the email address there, pmhackathon@snia.org. If you send a note to there, we'll get you credentialed and we'll actually get you on a system in the SNIA Tech Center with NVDIMM persistent memory in there, the PMDK, and some very simple tutorials that even if you have never programmed persistent memory, you'll be writing programs and getting them running probably within the first 5 or 10 minutes of getting on there. And then you have the ability to build from there. We will be coalescing at our Persistent Memory Summit coming up in January of 2020, and that'll be down at the Santa Clara Hyatt. And we also have other programs that we offer. The Non-Volatile Memory Workshop is a more academic workshop offered by UCSD in San Diego. But SNIA and UCSD have gotten together to do what we call persistent programming in real life, and we kicked it off last summer, and we had, I think, about 50 real-life programmers and architects that had worked on persistent memory, and this wasn't how would we do it, it's, well, we did this, and it hurt here, and it didn't hurt here, and this is why it's really cool to be involved in persistent memory. So we offer a bunch of experiential opportunities from programming to delivering and marketing on that experience. So we will be offering a variety of hackathon and workshop opportunities. The one I'll throw out here, and I think some of you might be interested, you don't have to wait to come to a hackathon. We'll have one at the Persistent Memory Summit, but if you've got a company, if you're a company and you've got some programmers, or if you have a programming community that you work with, if you can provide a venue and you can provide a date and that's a little bit of flexible, SNIA will actually come to you and we'll bring experts and we'll set up a hackathon system and we'll spend a few hours with you discussing the model, giving you an opportunity to play on the system so you can host your own hackathon. And again, the way to get to that, pmhackathon@snia.org. So, like I said, the NVDIM Programming Challenge is going on, and come by if you want to talk about that. If you want to talk about any of the other models at SNIA, we're happy to do that as well. I certainly thank you for your time, Arthur. That was a great conversation, and we look forward to seeing you for the remainder of the conference.
Thank you.
Any quick questions?
So feel free, we're right across the hall, stop by, we'll be hanging out for quite a bit of time here, so stop by and we can chat. Thank you.